We're now looking at higher order partial derivatives. Given a function with three independent variables, we can calculate the partial derivative of that dependent variable with respect to any of the independent variables. And if we're looking at the partial derivative with respect to x, that would mean that we're holding both of these other two variables constant in the computation. Another word about notation before we look at an example is that with the f subscript notation, notice that the variable on the left is x, that's what's going to be coming first, and then we differentiate with respect to y and z. So the differentiation order with the f notation goes from left to right. But with curly d notation, notice the variable that we're differentiating with respect to first is on the right. And if we're using curly d notation, the order of differentiation goes from right to left. So let's take a look at an example here. We have a function with three independent variables, and we're going to calculate the third order partial derivative. And I'll just zoom in here real quick to show you that in part A, we are first differentiating with respect to x, then with respect to y, and then with respect to z. And again with curly d, that's the first with respect to x, then with respect to y, and then with respect to z. So first, let's differentiate with respect to x. And if we're differentiating with respect to x first, that means that we're going to hold y and z constant. So here we calculate the first partial with respect to x. Now notice in this first partial derivative, both y and z are constant, and recall from Calc 1, if we had a constant in the denominator and we wanted to differentiate both sides of this, we would end up having just that constant as the derivative. And so since this denominator is all being held constant, we have 1 over y plus 2z as that first order partial derivative. Now the second thing that we're going to do is we're going to differentiate with respect to y, because that's in the center here. And when we differentiate with respect to y, we're going to hold x and z constant. So since y is in the denominator, I'm actually going to back up one step and rewrite this as being y plus 2z raised to the negative 1 power, because we're going to then take that and differentiate with respect to y. I think it's a little easier if we're using that power rule, which is going to be negative 1 times the y plus 2z, and then raise that to the negative 2 power, and then multiply by the derivative of the inside function, which is just going to be the derivative of y being 1. Again, the z value is being held constant, so its derivative is 0. So let's clean this up just a tad because we are going to have to differentiate this again, and I think I'm going to leave it with this power notation. Raising it to the negative 2 power is going to be easier to differentiate in our next step. The third variable that we differentiate with respect to is going to be z. Notice that that is here in the notation and on the far left if we had curly d notation. When we differentiate with respect to z, we're going to be holding x and y constant. So we're going to take this previous iteration and differentiate it now with respect to z. And again, we're going to be using that power rule. So our negative 2 times negative 1 is going to be 2 times y plus 2z, and then we raise that to the negative 3 power. Multiplying by the derivative of the inside with respect to z, the derivative of the inside is just going to be 2. So our final answer is going to have 4 in the numerator of the fraction. And let's now go ahead and put y plus 2z down into the denominator with a power positive 3, since this is our final answer. Now for part B, we're going to need to recall the original function was x over y plus 2z. And notice here, our order of differentiation is going to be first with respect to y, and then with respect to x, 2 times. So looking at the curly d notation, we see that the first variable of differentiation is over here to the right, and then the fact that we have curly dx squared means that we're going to differentiate with respect to x in the second and in the third iteration. So we begin by first differentiating with respect to y. So the first partial with respect to y, since y is in the denominator, we are going to need to use the quotient rule. We could turn it into a product and use the product rule, but I'm going to use the quotient rule. So we have the bottom times the derivative of the top. Now the derivative of the top, x is being held constant, and the derivative of a constant is just going to be 0. So that's bottom times the derivative of the top minus the top times the derivative of the bottom. Y is the only varying quantity and its derivative is 1. And then we're going to divide this by the bottom squared. So we definitely want to clean this up because we're going to have to differentiate it again. This numerator becomes negative x over the denominator, which is y plus 2z quantity squared. And now we're ready to differentiate with respect to x. And in order to do that, we'll hold y and z constant. So we're taking this previous iteration and differentiating it with respect to x. Now, let's notice again that if x is our variable and everything else is constant, then this derivative should be negative 1 over that constant. We could have used the quotient rule, but it's easier to notice that this is just x over a constant value. And finally, we're going to differentiate with respect to x again, which means that, again, we're holding y and z constant. So we'll take that previous iteration and differentiate it again with respect to x. But notice there are, this time, no x values in the previous iteration. Everything here is a constant, and the derivative of a constant is 0. So that would be our third order partial derivative.